Okay, in this lecture we are going to practice our solution for the sinusoidal steady-state response, and we're going to simply work some examples beginning with our familiar RRC circuit. We excite this circuit with a Vs of the form, let's say, 1 times cosine omega t, so this is a sinusoid, and we're looking for the response, the steady-state response across the capacitor. We have R1, R, and C, and the transfer function h of s that relates Vs to Vc, or Vc to Vs, is h of s equal to 2 divided by s plus 3. And we'll consider several cases of excitation. So first, we will consider omega equal to 0.1. So in other words, Vs is equal to 1 times cosine of 0.1 t. Now we can write that Vc is going to be equal to the amplitude of the excitation times the magnitude of the transfer function evaluated at omega equal to 0.1 times cosine of omega t, in this case 0.1, plus the angle of our transfer function evaluated at omega equal to 0.1. So let's go ahead and write an expression for the magnitude. We'll do this once, and then we'll use it for the various cases of omega that we'll solve as we go through this problem. So it's going to be the magnitude of 2, which is 2, divided by the magnitude of j omega plus 3, which is omega squared, square root of omega squared plus 3. The angle, we'll call theta, is equal to angle of h of j omega, will be equal to the angle of 2, which is 0, minus the angle of j omega plus 3, which will be omega over 3. So we'll kind of keep that handy. We'll use that several times. So h of magnitude of h of j 0.1 is equal to 2 over the square root 0.1 squared plus 3. Now 0.1 squared is 0.01, so it's going to be 2 over the square root of 3.01, which is approximately 2 over the square root of 3. And the angle, theta, will be minus a tan of 0.1 over 3, which is approximately minus 0.033 radian, or approximately minus 1.9 degrees. So therefore, our response is 2 over the square root of 3 times cosine of 0.1 t minus 0.033 radian. And of course this is approximately 2 over root of 3 cosine of 0.1 t. I mean, this is very, very small, 1.9 degrees. Alright, so what does this tell us? Let's take a step back here and consider that we have our system here, h of s, and we've applied a sinusoidal signal, has an amplitude of 1 and a frequency of 0.1. This is Vs, and the steady-state response, Vc, is essentially the same. Okay, I'm sorry, I have a mistake here that I just caught. Back up here, there's a square. This is 9. So that means this is 9. That means this is 9, and this is approximately 3. And this is 3. And this is 3. Okay, sorry about that. So we have a sinusoidal response that has a magnitude of 2/3 and a frequency of 0.1 as before. So essentially, if you apply this 0.1 radians per second sinusoidal signal into this network, the voltage you'll see across the capacitor is the same sinusoidal cosine signal, but with an amplitude that is 2/3 of what you put in. And if you think about that, that makes a lot of sense, because R1 was 2, R is 4. And if you think about that voltage division, let me just put it down here, where this is 2 and this is 4, if this is Vs, the voltage across here will be 4 over 2 plus 4 Vs, or 2/3 Vs. And that's essentially what is happening here. In other words, at this low frequency, the capacitor is not significantly impacting this voltage divider. And this low frequency sinusoidal voltage is passing through this network without really being affected, and it's merely the voltage division of the resistors that are affecting it. But now we're going to consider omega equal to 1. In other words, Vs is equal to 1 times cosine of 1 times t. Again, now all we have to find is h, the magnitude of h of J1, because we're exciting the system at a radian frequency of 1. And that is equal to 2 over square root of 1 squared plus 9, equal to 2 over square root of 10. And our angle, h of J1, is equal to minus the arctan of 1 over 3, which is equal to about 1 minus 0.32 radians, or minus 18.4 degrees. Let's say this is approximately 0.632. So therefore, the response, steady state capacitor voltage response, is 2 over square root of 10, or 0.632, times cosine of 1 times t minus 0.32 radians. So what do we have here? We have, let's draw this signal in the time domain. So we start off with a cosine wave here. Seen better. Okay. This is Vs. This is a magnitude of 1. And we are shifted, the response is shifted by minus 0.32 radians, which is approximately 0.1 times pi. Okay, so here a full half cycle, this would correspond to pi here, right? I'm doing time, but this would be pi, and 1/10 of that, it's going to be hard to show, but okay, we'll give it a shot here. All right, and our magnitude is 0.632, so we're down here at 0.632 right here, and we're going to be delayed a little bit. Okay, so this is Vc. So in other words, it is still sinusoidal. It's at the same frequency as the excitation, but now we see that it's somewhat attenuated. It's attenuated by a factor of square root of 10 over 2. It's scaled by 0.63, and it is lagging a little bit. It's lagging by 18.4 degrees, meaning it's not keeping up. It's trailing behind the sine wave that is exciting the system. Let's continue. Let's try omega equal to 3. So we have 1 cosine 3t. The magnitude of the transfer function will equal 2 over the square root of 3 squared plus 9, which is 2 over 3 square root of 2, which is equal to square root of 2 over 3. And the angle h of J3 is going to be equal to minus the arctan of 3 over 1. And that is approximately equal to, 3 over 3. Yep, 3 over 3, which is not approximately equal. It's equal to minus pi over 4, or minus 45 degrees. So therefore, the steady-state capacitor voltage response is square root of 2 over 3 cosine of 3t minus 45 degrees, or pi over 4. So now what do we have? If this was our cosine wave before, Vs, okay, now we're at a magnitude of square root of 2 over 3, which is 0.47. Okay, so we're somewhere around here, 0.47, and now we're lagging by a quarter cycle. So a quarter cycle is right here. So it'll come down here, it'll hit the peak. It's going to hit the 0 here. Okay, so it lags Vc, this is at omega equal to 3, lags Vs by 1/8. of a period, right? Because there's 2 pi in a period. It's lagging by 45 degrees. So we notice the trend. At 0.1 omega, the output was essentially the same amplitude, well, just 2/3 the amplitude of the input. At omega equal to 1, we saw that slightly attenuated from 2/3, which is 0.67, down to 0.63. Now at omega equal to 3, we're down to 0.47. So the amplitude is decreasing, and we're starting to lag. The waveform is now delayed a full 45 degrees. Now we want to consider omega equal to, we'll jump to something very big. Let's do 1,000. All right? Vs is equal to 1 times cosine of 1,000 t. All right? The magnitude, h of j 1,000, is equal to 2 over square root of 3 plus, or 3 squared, plus 1,000 squared, which is going to be approximately 2 over 1,000. All right, because the 1,000 squared is going to just swamp the 9. The angle of h of j 1,000 is going to be equal to minus a tan of 1,000 over 3. So now we're taking the arctangent of a very large number, and that will end up being very close to minus pi over 2, or minus 90 degrees. So we find that for this high frequency, Vc is approximately equal to 2 over 1,000 cosine 1,000 t minus pi over 2. So at this point, we have the signal significantly attenuated, and the phase lag has kind of bottomed out. We've reached this lagging of pi over 2, which would be 90 degrees. Recall that at omega equal to 3, the phase lag was 45 degrees. So evidently here we've gotten to 90 degrees, and I don't think we're going to get any further. For instance, if we say omega equal to 10,000, right, then you would have the magnitude of h of 10,000 would be basically 2 over 10,000. You could show that. And the angle of h of j 10,000 is approximately minus pi over 2, because again, you're taking the arctan of even a larger number now. In the limit that arctan, if you take the arctan of infinity, it's still pi over 2. So we would have Vc of t is equal to 2 over 10,000 times cosine 10,000 t minus pi over 2. And what we find in general, okay, we're continuing on, we would find that Vc of t is equal to 2 over omega times cosine of omega t minus pi over 2 for omega much, much greater than 3. And the reason I picked 3 is not quite clear to you at this point, but note that denominator of h of s is s plus 3, i.e. minus 3 is a pole of the system, of the transfer function. Okay, now that's some insight that you don't yet enjoy, but at least just by running these calculations over and over again for increasing omega, we see that asymptotically is what actually happens. And so what this circuit is really doing, okay, if I take this guy right here, and I'm driving him with Vs, okay, I could take the Thevenin equivalent here, right, where I would have, I'd have this would be Vs times 2/3, because this is 2 and this is 4, and this would be 4/3 of an ohm, this is 1/4 of a farad. Alright, and as I drive this with some sinusoidal cosine omega t, I find that for low frequencies, the output Vc is essentially the same magnitude as the input. It's 2/3 times whatever the amplitude is at the input. But as you go to higher and higher frequencies, this output will attenuate. So initially I've got something that looks like this, and then later on I've got something that looks, this is for low omega, this guy here is for large omega. And if you think about it, when we apply, we ask the question, or we talk about a capacitor being open for DC, Okay, it's like a short circuit for DC. And so the lower the frequency that you excite this at, the closer you're approaching a DC voltage. And so the capacitor acts like an open circuit, and this voltage divider, this impedance of the capacitor divided over the impedance of the cap plus the 4/3 resistance, tends to be a ratio of 1. But as you go to higher and higher frequencies, this voltage division, which is in the end 1 over SC over 1 over SC plus 4/3, right? This, where S is equal to j omega, the magnitude of this ratio tends toward 0 as we go to higher and higher frequencies. And that's in keeping with basically the impedance of the capacitor, Z of C, which is 1 over SC, tends towards 0 as S gets larger and larger and larger and larger, where S equals 0 is DC, right? So S equals 0, impedance of the cap is infinite. Now when S gets very large, the impedance of the capacitor goes towards 0. And so if the capacitor is involved in this voltage divider, it makes sense that as you excite the system with higher and higher frequencies, the magnitude of S, albeit that it's j omega, it's complex or imaginary, the magnitude of S, which is omega, goes higher and higher and higher. The impedance of the capacitor goes smaller and smaller and smaller. And so in this voltage divider, you're basically getting this ratio, impedance of the cap over the sum of the impedances, that tends towards 0. And that's exactly what we've experienced by running the numbers for these various angular frequencies. All right, let's consider one more example. And here we will use a capacitor and a resistor. And we're going to look for the voltage across the resistor when we excite the system with the voltage Vs. We have a capacitor C and this resistor R. We'll say that the capacitance has a value of 1 millifarad and the resistance has a resistance of 1 kiloohm. And we note that R times C is equal to 1 milli times 1 K, so it's equal to 1 second. Now we're going to express, using impedance, we're going to express VR as a function of Vs. This is a voltage divider. Right? We can transform this into ZC and ZR, where we excite this with Vs and we're looking for the voltage VC. I'm sorry, VR. Take that back. VR. So we'd say VR is equal to ZR over ZR plus ZC times the excitation, which is going to be R over R plus 1 over SC Vs, which will be, when multiplied through by SC, be SRC over SRC plus 1 times Vs. So therefore, plugging in numbers, we have VR is equal to S over S plus 1 times Vs. In other words, H of S, the transfer function for this system, is S over S plus 1. So given that Vs is equal to sine omega t, find VR. Okay? Now we've been using cosine excitation, but nothing changes if it's kind of just changing your reference point. If we're exciting it with a sine as opposed to a cosine, I would expect my response to be magnitude of the transfer function times sine, not cosine, because I'm exciting it with a sine, omega t plus angle of the transfer function. All right? So let's let omega equal 1. In this case, we'll have the magnitude of h of j1 is equal to j1 over j1 plus 1, magnitude of that. So it would be 1, the magnitude of j, over the magnitude of j plus 1 is 1 squared plus square root of 1 squared plus 1 squared. So 1 over root of 2. The angle of h of j omega, well, h of j1, is going to be equal to, actually let's do it in terms of j omega, we should write that once here, is going to be the angle of j omega, that's the numerator, minus the angle of j omega plus 1. Well, the angle of j omega, that's a line that lies on the vertical axis. This is real, this is imaginary. Right? This is omega. So the angle of that is pi over 2, or 90 degrees. So this is going to be pi over 2 minus the arctan of omega over 1. Specifically, the angle of h at j1 is going to be pi over 2 minus the arctan of 1. which is equal to pi over 4. So pi over 2 minus pi over 4 is equal to pi over 4. Therefore, our resistor voltage will be equal to 1 over the square root of 2 sine of 1t plus pi over 4. This is 45 degrees, by the way. Okay, this is at omega equal to 1. What about omega equal to 10? Right? At omega equal 10, we would have the magnitude is going to be equal to 10 over square root of 10 squared plus 1 squared. So that's 10 over square root of 101, which is approximately 10 over 10, or 1. The angle of the transfer function will be pi over 2 minus the arctan of 10, which is pi over 2 minus 0.1, it's 1.47 radian. This is 1.57. So this is approximately 0.1 radian. 0.1 radian. So we have VR of t is equal to 1 sine of 10t plus 0.1 radians. Let's try 100 radians per second. The magnitude here is going to be 100 over square root of 100 squared plus 1. This will again be approximately equal to 100 over 100, or 1. The angle will be pi over 2 minus the arctan of 10 of 100, which is going to be equal to, or approximately equal to, 0.01 radian. So we'd have VR of t is approximately equal to 1 sine 10t, 100t, plus 0.01. And if we did 1,000, we would find VR of t is approximately equal to 1 sine 100t, 1,000t, plus 0.001. So we found that we started at omega 1. We found that the amplitude there of the output was 1 over the square root of 2, or 0.707, that of the input. And the signal was shifted, not lagging, but leading by pi over 4. Okay, so let me go back and actually draw this case, omega equal to 1. What we have is, we have a sine wave here. This is Vs. It's be an amplitude of 1. The amplitude 1 over square root of 2, 0.707 is right here. And we have a lead of pi over 4. Okay, so we're actually going to hit a peak here. And this will be like this. And then we're going to hit this peak here. And so the voltage on the resistor is actually finding its way to a peak before the input voltage finds its way. All right, so this is VR. Now think about this. Let's go back to the circuit. Say this is equal to IC times R, right? Because these are in series. And we know that the capacitor voltage VC is equal to 1 over C integral of IC dt. Right? It takes current over time to integrate and produce voltage on the cap. So what you're really seeing here is that as you drive this circuit with a voltage source, there is a current that leads that voltage, and that is needed or required by the capacitor in order to assist the capacitor in keeping up with the voltage that's being applied across the resistor and capacitor network. Let's try a frequency below 1. Let's try 0.1. In this case, we'd have the magnitude of H is going to be equal to 0.1 over square root of 0.1 squared plus 1, which is approximately 0.1, right? Because the 0.1 squared is 0.01, and that's swamped out by the 1 in the radical down there. And then the angle of H will be equal to pi over 2 minus the arctan of 0.1. which is approximately pi over 2 minus 0.1 radians. So this is 1.47. Let's try 0.01. We can show that the magnitude here is going to be approximately 0.01, and the angle will be approximately 1.56. In other words, just 0.01 off of pi over 2. So let's plot these responses here on the next page. What we're going to do is we're going to plot the magnitude of h of j omega. In other words, this is the magnitude of the capacitor resistor voltage divided by the magnitude of what we have excited it with. All right, this is the constant proportionality between the exciting amplitude or magnitude and the response magnitude. And we can plot this on, let's go 0.01, 0.11. We'll do it on a log scale and a horizontal because we covered quite a range here. Okay, so this is omega. And we have 1 here, and we'll say 1 over square root of 2 here. And down here we have 0.1 and 0.01. All right. We found that at an omega of 1, the magnitude of the transfer function was 1 over square root of 2. We found that at 10, it was approximately 1, and at 100 it was approximately 1, and at 1,000 it was approximately 1, and so on. At 0.1, we found that the magnitude was approximately 0.1 and then 0.01. Okay, so if we connect the dots here, what we find is that this is actually this is the frequency response of the cap resistor network. And what this tells us is that if you excite this network at the input of this two-port network, an input port and an output port, that frequencies that are much lower than 1, okay, are filtered out. So signals, or sinusoids with omega much less than 1 are blocked. Right? They're blocked from passing through. Passing through, and I'll call this a filter. Okay? It's the first time I'm using that term. It's just a term for this network that happens to, it essentially filters. It doesn't allow sinusoids through that are much lower frequency than 1 radian per second. And sinusoids with omega much, much greater than 1 radian per second are passed on, or passed through, unattenuated. This is called a high pass filter, because it passes the high frequencies and it attenuates the low frequencies. And this is really your first, I guess, view of this whole notion of doing frequency response analysis. I told you that this whole concept of impedance will open the doorway for us to be able to look at the circuits in a different light. Instead of studying them as a function, or their responses as a function of time, we can study their responses as a function of the frequency at which we excite them.